All right, this whole video is about one inequality, a single one, and it's a big one, okay? The idea here is that not every three numbers can make a triangle, okay? And I give a really simple example here. If you have one side that's of length 10 and two little tiny ones, that there's no way for them to bridge the gap of 10, right? I imagine it like a T-Rex trying to clap. He's going, I can't, I want to, but he just can't put those paws together, those claws. All right, so that's the big idea here. So to cross a 100-foot wide river, you need more than 100 feet of bridge, right? If you had exactly 100 feet of bridge, you'd set the bridge right here, and it would just go, and it would fall right through, right? You need a little bit extra on the sides, or if it's a triangle, we need to go up a little and down a little and not have it be a straight line. Okay, put another way, here's the inequality. If I have three sides of a triangle, and this side is the river, then A plus B has to be bigger than C. And then we go, wait a second, well, what if the other side's the river? And then we just say, well, sure, I could take this thing and spin it around. Actually, when you rotate a B, it looks like an A. But either way, the B on the bottom is now the river. And so if B's the river, then A plus C is bigger than B. And then we rotate it again and say, well, now A's the river. And so B plus C have to get across that river. So either way you look at it, whatever side you're talking about is like the conceptual river, the other two have to be able to cross that river. That's the big idea. And I'll write it out in a specific way. We'll do tons of examples, but that's the idea of this whole thing. Okay, first, two small little theorems and definitions, okay? So the shortest distance from a point to a line is the perpendicular. And I write the proof here. I'm not going to walk through it for interest of time, but the idea is simple. We just say, well, if this is the perpendicular, and here's a non-perpendicular, well then this is a right angle, and in a triangle out of 180 degrees, any other angle is less than 90, right? We literally just go, oh, well, there's 90 degrees left over between two angles, so the very definition of an inequality says the other angle, let's call it angle A here, then is less than 90, so it's something less than 90, which means this is a smaller angle opening up to a small side, and this 90 is a bigger angle opening up to a big side. So that means the smallest side is the perpendicular, and no matter what other side you make, it's always going to form a right triangle where the hypotenuse here is longer than this small leg that's the direct path. So shortest distance from a point to a line is the perpendicular. And then we have the exact same thing with a plane, and for the exact same reason. Here's the perpendicular, here's any other path to the plane, and then here's a triangle. Done. Then same proof, right? And so the way we define the distance from a point to a line is the shortest distance. So if I say, what is the distance from this point to this line? We go, oh, well, first I need to make the perpendicular segment here, and then I just need to find its length. That's the very definition when we say the words, the distance between that point and that line. This is similar to if we say, what's the distance between two parallel lines? I mean, the distance between two non-parallel lines is 0 because they hit each other here. But the distance between two parallel lines is any point on this. It's the shortest distance to this line or the perpendicular. So that's the distance between two parallel lines. And if they're, now, I have not even heard the phrase distance between skew lines, but the distance between two skew lines would just be the closest distance they ever arrive. That would be an interesting problem. I have never done that problem. That would be really cool. Anyways, the definition of distance from a point to a plane is the same. It's the shortest distance, perpendicular, straight at it. Now, this brings up a whole concept of orthogonal versus perpendicular. Orthogonal means perpendicular, but more dimensions. Because you could have a plane here, and you could have a line that comes in, and it's perpendicular this way, and yet this direction, it's like 30 degrees, right? If you think about it, you could stand like, here's a plane, take a sheet of paper, right? Okay, so take the sheet of paper and lay the corner so that it's like this. Well, this edge here is lying on the plane, and this edge here is sticking out into space. Oh, I'll do that in pink maybe. So this edge here of your textbook or paper is laying on the table, And this end is sticking off the table, so this forms a right angle. You're sure that forms a right angle because it's the corner of your book or your paper, and yet your book could be tilted at any angle. So actually, when you get into 3D space, just perpendicular, like two lines perpendicular, is not enough to say a line is perpendicular to a plane. You have to have it's perpendicular in two different directions. So here's one, and then here's that. Now we could be certain that it's orthogonal. So in any direction toward this plane, it's going to be perpendicular. That's a cool concept. All right, now back to the inequality. So here's the inequality written out. We're given any triangle, and it says any two sides you add up must be greater than the third because they have to cross the river. That's it, right? And then if I look at it from a different perspective, these two are bigger than this river, and similarly, these two are bigger than this river. So we just write out all three of those inequalities. Notice, though, that none of them say or equal to. It's always just greater than. Because if they were equal to, that statement A plus B, or AB plus BC equals AC would literally mean the very definition of betweenness, or the segment addition postulate. So B would be between A and C, and it would be a segment, not a triangle, and it would look like this. So if we have 3 plus 5 equals 8, there's no extra room to go off of that segment for B to be up here. If we were to travel off of the straight line to get to B, there would have to be some more distance, right? It would have to be like 3.1 and 5. So like there would have to be some extra teeny amount of space, and now we can go out of the way. But if exactly 3 plus 5 equals 8, it's just a line segment, no triangle. All right, so here's a couple just yes or no's, all right? So for number 4, let's check. Is 5 plus 4 bigger than 3? Is 5 plus 3 bigger than 4? And is 3 plus 4 bigger than 5, okay? Those are the three things we need to check. So any two sides need to be bigger than the other side. So check, 9 is bigger than 3. Check, 8 is bigger than 4. Check, 7 is bigger than 5. Yes, this is a triangle. Or these can form a triangle. And by SSS, every triangle with these sides would always be congruent to every other. All right, let's check the next one. So for 5, we have 5 plus 15 is bigger than 10. We have 5 plus 10 is bigger than 15. And we have 10 plus 15 is bigger than 5. So check that's true. Check that's true. But uh-oh, these equal to one another. So this is actually no. This is a line segment, right? So yes, they could connect, but the connection would be like this. Here's a total of 15, here's 5, and here's 10. So it would just form a segment. So it's like you're trying to cross the river and they exactly touch in a perfect straight line, but we just don't have a triangle that's formed. Okay, so the next one. Maybe you're starting to see a pattern here that really, and this is what I mentioned just right below, is if you know all three side lengths, you only really need to check one thing, right? You only need to see if the two smaller lengths are enough to cross the big river, because obviously big plus anything is bigger than medium, because big's bigger than medium. So that one is already true, and big is already bigger than small, so that one's true. So we don't need to check if big plus something is bigger than a small side. So up here, we didn't need to check if 5 plus something was bigger than 3. 5 is always bigger than 3. And same thing here, 5 is always bigger than 4. Really, we just needed to see if the small two cross the big. Right here, 15's already bigger than 10. 15's already bigger than 5. We just needed that one. So now when we get to 6, we say really all we need to do is line these up in order and go, is the smallest plus the medium one big enough to get across the longest side? This is 30.9 is bigger than 31. No. This not enough to span, so this would look something like this, where they're not able to span the gap. And then 7, we would do the same thing. We go, is 5.2 smallest plus medium big enough to go across the 10.1? So this is 10.8, bigger than 10.1? Yes, check. Because any others I try, are these two bigger than 5? Yes. Are these two bigger than 5? Yes, because 10.1 by itself is bigger than the other. All right, so that's just a little shortcut you could notice. But sometimes we're not given all three sides. Sometimes we're only given 2. So now let's say we have these two and some side x. And over here, let's call it, I don't know, and call it y. All right, so we're given 3. Well, now, since we don't know all 3 sides, we do have to write all 3 inequalities. So we know 7 plus 12 has to be bigger than x. And we know 7 plus x is bigger than 12. And we know x plus 12 is bigger than 7, right? So these are the 3 inequalities we know must be true. And it says find the range of measures for the third side if you have a triangle. That's the key. If you have a triangle and you have 2 sides of a triangle, you know these must be true. So I'm going to go ahead and separate these now, okay? Because I'm going to solve them. So I'll put this one over here, and then I'll put this one over here. And we're kind of taking up some of the room from the next problem. So this is, 19 is greater than x. Here we subtract 7 from both sides, which we can totally do. The only thing you need to be aware of is multiplication or division by a negative number. Okay, so we subtract 7 from both sides. Here we subtract 12 from both sides. All right, so now all we have to do is put this into order. So let's say we've got a number line here, okay? And I'm not going to really number a lot of things here, but we have a 19, and x has to be less than that. So no bubble there, can't be 19, but it has to be on this side. And then it's got to be bigger than negative 5, so here's negative 5, okay? And it's got to be bigger than positive 5. So here's positive 5, it's got to be bigger than positive 5. So what's the only region where all 3 of those are true? Well, that's this region right here is the only region where all 3 are true, right? And so the answer here would be x has to be, and we could write this as one compound inequality, meaning it's really 2 separate things together, but we could say x has to be between 19 and 5, which is really the same thing as saying x is greater than 5 and x is less than 19. All right, so I'm going to take all this and shrink it a little so we have room to do our other problem here. So let's just put it off to the side here. All right, we'll draw a little shoop. Okay, now let's do the next one. So same thing on another problem. So over here we got 3 separate statements. So 14 plus 23 is greater than, has to cross the y. And then also y plus 14 has to be big enough to cross the 23, and y plus 23 has to be big enough to cross the 14. All right, so let's go ahead and do this then. So the first one says that's 37 is bigger than y. The next one is y is greater than, and we subtract the 14. So that means we have 9 left over. And then here we subtract the 23, so we're bigger than negative 9. Well, if we have to be bigger than 9, then of course we're already satisfying this, right? Like, so of these two, if both have to be true, that's the same as just saying x is bigger than 9, because we can't be negative like 2. Sure, that makes this one true, but it doesn't make this one true. So the only, like, we can throw away that extra one, or you can do as we did on the left and do the entire, like, draw it all. But all right, let's do this now. So putting these two together, we get y is less than 37 and y is greater than 9. Or another way to write that is y is less than 37 but greater than 9. Remember, it's not or equal to. Another common mistake here is kids just list. They're like, it can be 10 or 11 or 12 ... all the way up to 35 to 36. But actually, there's infinitely many more values between 10 and 11. It could actually be like 9.1. It could be 9.01. It could be 9.00000. So it's any number between, or any real number between 9 and 37. Okay, good stuff. Just wanted to make sure, because sometimes kids list values instead of, it should be an entire range of values. All right, so explain why the distance between 2 non-horizontal parallel lines on a coordinate plane cannot be found using the distance between their y-intercepts. So in other words, I'm going to just draw this to the side here. It's saying on the coordinate plane we have 2 parallel lines that are not horizontal. So here's 2 parallel lines. It's saying, why can't we use the distance from the 2 lines to say it's the distance from here to here, their y-intercept? The reason is the distance between 2 parallel lines, just like the distance between a point and a line, is the perpendicular, the shortest path. Because otherwise you'd say, well, the distance between these parallel lines is, I don't know, 10 this way, 9 this way, 8 this way, where it's perpendicular. Or you could even do it a super diagonal one, be like, it's 100 distance. So it's super ambiguous. So instead we define the distance to be the shortest path. And since these are not horizontal, then we know the vertical there between the two y-intercepts is not perpendicular. And so that's not the shortest path. So that's the reason why. All right, so in this problem, it says they drew this triangle with these values. What's the problem here? Well, the problem here is if we have a big river, we need to be able to cross it. 15 feet of bridge definitely crosses a river of 13. Here, though, we have a river of 13, and we only have 13 feet of bridge. Why, that's exactly a line segment. That's the very definition of E being between F and G. So if you redraw this correctly, this is actually F and G that are 13 apart, and then 5 along that journey from F, you hit the point E. But this is 5 and 8. 5 plus 8 equals 13. It's the very definition of E being between F and G. So that's why it's not a triangle, it's a line segment for Inoki. A cool name. All right, and then find 3 numbers that can be the lengths of sides of a triangle and 3 numbers that can't. So again, all we need are 2 smallers that are bigger than the big. So let's go 3, 4, 5. Okay, so 3, 4, 5. And then over here, let's do something where we can't. Let's get extreme. Let's say we have a 100-foot river and we have a 1-foot board and a 2-foot board. That's not enough to get across the river. So there's 2 examples of one that does work and one that doesn't. All right, so here's a bunch of yes or no's. Okay, so I'll challenge you to pause here and try some of these on your own. Maybe even trying to work backwards and find one that does work and find one that doesn't work, right? So for example, I'm going to say I can identify that this one doesn't work because 2 plus 6 is not bigger than 11. So I know this is a no right away. All right, let's see. Can I find any other ones that I know don't work? Oh, I found another one here. 9 plus 5 is not enough to cross 17, so that's a no. Maybe are there anywhere that's exact? Oh, look at this one. This is a line segment. So no, it's not. It's a line segment. They do connect, but that's the very definition of betweenness. So no, that's not it. And then we could keep looking, but for this one, the smaller 2 do add up to be bigger than the biggest. Yes. Here, the smaller 2 add up to 39, so yes. Here, the smaller 2 add up to 16, so yes. Whoa. And then here, the smaller 2, 29, yes. And then it just gets to be decimals, which aren't scary. You add them together. These 2 add together and make 10.7, so yes. And you just keep going with that, okay? Oh, over here, look at this. This one, 13 plus 16 is exactly, 29. No, that's another one of those line segments which exactly meet, but there's not enough extra space to make a triangle. There's only just the connection to exactly form a segment. All right, now let's do it with unknowns, okay? Let's do a couple. What about this one? All right, well, you know, let's just label the other side x. You know it's 99 and 2 and x, so 99 plus x is bigger than 2. 99 plus 2 is bigger than x, and 2 plus x is bigger than 99. So subtracting over here, we get x is bigger than 97. Over here, we get minus, we get x has to be bigger than negative 97. And over here, we get x has to be less than, I reverse the order, really, this is 101 is bigger than x, but x is less than 101. So we can toss this one out, and we get x is between 101 and 97. Now, maybe people are starting to see a pattern. If we start with the sides 92 or 99 and 2, how could we get these numbers? Well, the maximum, right? So if I have a side of 99 and a side of 2, the furthest, the longest this could be is if I make these basically straight. I open these sides up almost to their segment of 101, but it can't equal 101, right? And so really, the longest it could be is the 99 plus 2 length of 101. And what's the shortest? The shortest is if I bring these close together, bring them close together, and I end up saying, I'm still going closer together, and what I end up getting is here's a 99, and then the 2 is essentially laying right on top of it, and so there's 97 left over. And so really, this is just 99 minus 2 is the shortest, and 99 plus 2 is the biggest. So if I take any 2 right here, I could say x has to be between 18 minus 12, and 18 plus 12. So really x just has to be between 30 and 6. And that's a nice little shortcut you could do to get that one. Okay, so you're like, oh, well then I got this. Oh, I so got this. Oh, what? 9 and 7. You think you're so good. Okay, so x is less than 7 plus 9 and bigger than 9 minus 7. So it's between 2 and 16. I could do every problem ever. Okay, what if there's no numbers? What? What? Okay. What do we know? What do we know? Okay, for this triangle to exist, every of the inequalities has to be correct. So let's write it out. So we know 2x plus 1, that's one side, plus another side has to be bigger than the other side, right? We know that's true all three. Okay, so let's write it out. So let's see, 2x plus 1 plus 4x. Oh, it was minus 7, and I wrote plus 7. That would have been an error. Okay, so 2x plus 1 and then 4x minus 7. Those two add together to be bigger than x plus 1. And then the last side I'll do on the left here. Now I'll just do it below in the middle, okay? And then the last one is the x plus 1 side plus the 4x minus 7 side has to be bigger than the 2x plus 1 side. Okay, so we know all three of these are true. We actually know something else, though, right? What else do we know? And we could even, maybe we know things like this is a 60 and this is a 70, so we know this side is bigger than this side. Maybe that sort of thing happens in the problem. We don't in this problem. But we do know this is the side of a triangle. What do we know about the numerical value of the side of a triangle? A side length, a segment length. For it to be a segment, it has to be positive. So over on the left, we could just write all of these segments. X plus 1 has to be bigger than 0. 2x plus 1 has to be bigger than 0. And 4x minus 7 has to be bigger than 0. So these are the 6 inequalities that we know, and we have to solve all 6 to get a number. So let's do it. First, I'll do the ones on the left here. X is bigger than negative 1. 2x is bigger than negative 1, so x is bigger than negative 1/2. And 4x is bigger than 7, so x is bigger than 7/4. Again, if it's bigger than negative 1 and bigger than 1/2 and bigger than 7/4, we can just take this one because that one satisfies all three. If it's a positive number bigger than 1.75, well then it's already bigger than negative 1 and bigger than negative 1/2, so it satisfies all three automatically. Okay, so we got that one. Now let's go up top, see what else we got. So we got 3x plus 2 is bigger than 4x minus 7. I'm going to subtract the 3x so I don't have to deal with any negative coefficients. And then I'm going to add the 7 to both sides, okay? So that's x is less than 9. Now notice I could have done this without avoiding the negative coefficients. I could have moved it the other way. So I would have had negative x is greater than negative 9. And then I would have had to divide by negative 1, and I would have had to switch the sign. Anytime you multiply or divide by negative 1, I'd switch the sign. So either way, I get x is smaller than 9. I just like doing addition and subtraction and not dealing with the switch sign. So I'm always going to add or subtract so the x's end up on the side where their coefficient's positive. Okay, so 6x minus 6 is bigger than x plus 1. I'm going to minus the x, so it's on the left here. I'm going to add the 6 to both sides, so I get 5x is bigger than 7. And then x is bigger than 7/5. No switching the sign because I divide by positive. 5x minus 6 is greater than 2x plus 1. I'm going to subtract the 2x's. Okay, and then I'm going to add the 6. And I get 3x is bigger than 7, so x is bigger than 7/3. Okay, so now I just got to combine all these. So here's the one where x is smaller than something. That's the only one where x is smaller. So part of our answer is x has to be smaller than 9. And then the question is, what does x have to be bigger than? Well, x has to be bigger than 7/5 and 7/3 and 7/4. That's funny how it all works out that way. So which of those is most restrictive? Well, think about that. This is around, right, 2.3 repeating. This is around, I'm saying around, it's actually exactly 1.4, and this is exactly 1.75. So which of those, right, if you divide 7 into 5 pieces, it's small. Divide 7 into 4 pieces, it's less small. And divide 7 into 3, it's bigger. So it has to be bigger than 7/3. So that's our total final most restricted between all of these 6 inequalities, the only region where all 6 are true is between 9 and 7/3. So I'll do one more problem like that, and then I'm going to prove the triangle inequality theorem, and that's it. All right, let's do one more problem like that. So again, if we have these 3, we know the 3 inequalities are y minus 1 plus 2y plus 1. I just made this one up, so we'll see if maybe it'll work out to an impossible scenario. It might be if we solve for like y is bigger, we might get y has to be like bigger than 2 and y has to be negative, which is impossible. So you'd say there's no values of y where this is a real triangle. It might happen. I just like threw random values in here. Okay, and then let's see over here, we get a different combo. So y plus 1 plus 3y minus 2. So y minus 1, 3y minus 2 is bigger than 2y plus 1. Well, that's really off to the side there. And then last one is, which combination am I just doing? Y minus 1 on the other side. Okay, so 2y plus 1, 3y minus 2, bigger than y minus 1. All right, there's the combos. Let's solve them in a different color. Now let's write the other ones too. Y minus 1 is positive, 2y plus 1 is positive, and 3y minus 2 is positive. Okay, we're going to solve all these. So let's do the easy ones first. So y is bigger than 1. 2y is bigger than negative 1, so y is bigger than negative 1/2. And 3y is bigger than 2, so y is bigger than 2/3. Well, if y is bigger than 1, then it's bigger than 2/3 already, and it's bigger than negative 1/2 already. So we only need that y is bigger than 1. All right, then we go over here and we'll just solve. So we get 3y, and plus nothing, is bigger than 3y minus 2. So we get, subtracting the 3y for both sides, we get 0 is bigger than negative 2. That's always true. So check, any y value makes that true. Well, that was easy. Okay, so that one's always true. Then over here we get 4y minus 3 is bigger than 2y plus 1. So we get, subtracting the 2y, we get 2y, and then we add 3 to both sides. We get 2y is bigger than, sorry, I crossed that out. I did not mean to cross out. So 2y is bigger than 4, so y has to be bigger than 1/2. Got it. And then down here we get 5y minus 1 is bigger than y minus 1, making sure. So 5y is bigger than y. Now we subtract the y. This is where people go, oh, always true, no solution. So we subtract y. This is 4y is bigger than 0. We divide by 4, and we get y is bigger than 0. Whoa, and so what would have been our limiting one here actually was always true, so there is no upper limit. So y is bigger than 1/2. Y is bigger than 0. So any value bigger than 1. So actually, any value where y is bigger than 1 will always be true. And notice here, because we never had like a minus y or something, making it go down, any value as these get bigger will actually end up working, because you have the y plus the 2y and the 3y here are always going to be about in a certain range together. So this is going to be a certain kind. Oh, that's really cool. What an interesting one, where this one always came out to be true, because 0 is always bigger than negative 2, because the 3 y's on both sides canceled out. And so that was just an always true inequality for any value of y. What a cool problem. All right, so the last thing, I'm just going to show you the proof. I'm not going to do the whole proof, but here's the idea. If you start with any angle in a triangle, right? So you have a triangle and any angle. Now, what we can establish then is that any two sides are bigger than the third. So you would just repeat this for, angle BCA and for angle, why did they even call it? Just call it angle B. And then for angle C and then for angle A, right? So you could just repeat this for all three angles, and then you would get all three different inequalities of two sides out to be bigger than the third. We chose an arbitrary one, but the proof works for all of them. So here's what you do. You extend the side. Okay, so we start with angle ABC, and all we do is extend one of the sides so that these are the same. And you can always do that. Literally, you just extend the line, and whatever length this is, you go that far along the line. Can you extend a line or a segment? Can you extend it? Yes. Does this have a number length? Yes. Can we go that far on a line? Yes. So we can absolutely do that no matter what, right? Like even if it down here on the left looks more like this, we could still extend C out here, and then just whatever length this is, that's how far we go. So that's the auxiliary set that we add, okay? And it gave you that hint there. So we know that CA is equal to CD, or we know that CD is congruent to CA, however you want to word it. But that was by how we created the auxiliary set, right? That was how we put the D into the picture, so that's something that we know. All right, so we start with those two segments being the same means that those sides are the same by base angle biconditional. Okay, so then the measures are the same by the definition of congruent angles. And by the angle addition postulate, we could say, oh, let me just clean up this diagram up here. What we could say then is the top angle here is just like piece plus piece equals whole angle. That's just the angle addition postulate. Nothing really special there. Okay, so we can add up and say the top angle. But then since we have these two angles are the same, and we just said that this piece plus this piece add up to the whole, we can just substitute out this angle for its equivalent angle here. Okay, so we substitute that out, and now we have BAC. So we have this angle plus this angle adds up to the whole angle. Now, why are we doing that, okay? The reason is just to get an inequality, right? If we have this, reverse order. If we have this angle plus something equals this, that's the very definition of an inequality, right? As long as we're adding something positive, that means we're getting to a bigger number. That means BAD has to be bigger than this because we added a positive number to get there. That's the very definition of an inequality we did last video or the one before, right? Okay, so we have that inequality, and then we could use like our law of sines. So if we look up here and we go, okay, well, and let me clean this up again. So if we have CDA now, if we have CDA is bigger than, just go down here, BAD. So if we have that's bigger than this is small, right, BAD. So just, oh, sorry, I reversed that. If we have BAD is big, and this is small, so big and small, and of course it's bigger than this because the small angle is the same as this. So of course the whole angle is bigger than a part of it, right, because these two are the same. So yeah, of course the big angle, the whole angle is bigger than a piece of it. So yeah, we got big and small, but that means this side is big compared to this side is small. That's our little law of sines, right? So now we could say BD is bigger than BA. Got it? But then over to the side, the way we constructed this segment is this whole thing on the bottom, BD, is just BC plus BD, right? So if we now have that this whole side is big and this is small, okay, and we know that this plus this is equal to the whole segment, which we wrote right there, then we could just do some substitution and say, well, then I could replace this BD with this, because that's the same as BD. Okay, so we're getting there. We're really close. So now we say, okay, well, we've got BC plus CD is bigger than AB, but we didn't have a D in our original problem, right? We didn't have this D. So how could we replace this segment? Well, the way we constructed it was to be the same as this length. And so we just replace that CD with a CA. And that's where I see that arrow coming all the way from up here at that thing we were given. So bring it down and we replace that and boom. We just proved it. What? What a good ending to the video. All right, guys, enjoy.